Okay, so part of this has some review, so we're going to skip that and let you, it's got some extra practice that you can do on your own on example 1 of creating matrices, etc. I'll pause here just to highlight something. So one of the issues we saw last time was we wanted to give you guys the answers so that you could check things against, but then when you were trying to do something, you guys pointed out, the answer is like the line below, so we don't have to think very hard about where to put the parentheses and stuff. So Lou and I yesterday came up with something a little bit different. So what we're doing is we're doing a sequence of little things so that you can't see what this almost zero vector is supposed to be. I mean, it's not that complicated, right? You're supposed to make a vector that has 5 entries in it. It's a column vector, and the third entry is minus 1.5. In other situations, it'll be a little bit more complicated, but instead of just having what the Autograder cell would have, we just put in some tests using things that we haven't covered, like the norm and stuff. Don't worry about that. But what we've done is we have it set up so that if you get everything right, these tests will come out and then it will say nothing, nothing, nothing. That means nothing's wrong, so everything is good. Okay, so the answer is not given away, but you have high confidence if when you run this with the answer in and this goes nothing, 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 that nothing is wrong and your answer is almost surely right. So, and what we're going to do after homework 2, maybe we get it into homework 2, but probably starting with homework 3, is today, given our experience with these, if you kind of like them, then what we'll do is we'll put in some of these before the Autograder cell is run, so you can kind of check your answers and go, okay, I've done 6 of them of the 12, and I've got feedback that my answers are really on track. Or it's not, it's failing the test, and then I should really reach out on Piazza and stuff like that. Okay, so that'll be the idea, instead of just having the answer in the lab ones, and we'll do that in the homework as well. So we're going to start here, assuming our vectors are already created. And remember, we've got 2 types of vectors. We've got row vectors. Okay, so we got row vector 1, 3, 5, 7, 9. These are vectors that you would have built up in an example 1. Almost zero vector. We've got using random, just because we're going to create some random matrices. We set the seed in this because the way random works, every time it runs, it pulls up a new random matrix. That's what you want. It should be random. It shouldn't be repeatable. But if you run the code a couple of times, getting it debugged, we don't want you having a different matrix every time and getting a different answer and not being able to check against us. So what we do is it's called setting the seed that the random number generator is using. And if you set the seed all the time, then it will always produce the same matrix here. Now, I don't know what matrix that's going to be because it's randomly selected, but once you fix the seed, there's a really nice algorithm that does that. Okay, so given a row vector 1, 3, 5, 7, 9, if you want to pick out any element, this one has 5, you just use the index. And what we're emphasizing here is that Julia is a 1-indexed piece of code, and the first element starts with a 1, whereas Python would start with a 0, C++ would start with a 0, MATLAB would start with a 1. Okay. Whoops. Everybody got things open where I should have asked. Everybody got things open. We're good. LumiDesk is working for everybody. Whew. And we understand the idea of a row versus a column. Who do you think we are, Professor Grizzle? No, just making sure. Okay, so in the beginning, okay. And then if you want this vector that's almost 0, so it's got 0, 0, and this time minus pi instead of minus 1.5, 0, 0, 0. So we've got 1, 2, 3, 4, 5, 6, 7 entries. And if we want to select the non-zero number from the almost zero vector, then we'd want the 1, 2, 3 entry, and so num equals almost zero vector of 3. And that will, if you run that now, so we can either hit run. It's going to be a little bit slow because it's getting the random package going. And since I'm holding the mic, it's harder for me to hit control shift. But if you just hit shift enter, excuse me, that's the same thing as doing a run. And then here, bingo. And we get minus pi, okay. So, and if we'd have messed up and put in 8 and we run it, it was going to tell us that that's not good because we have a bounds error. We attempted to access index 8 of a 7-element vector. Okay, so that's what the error message is telling us. And that'll happen because you will create something in a cell and then you will forget to run it, and then it will use something that you defined previously, and you go, why does that vector have length 3 when I see on my screen it's length 7 or whatever? Okay, so that's what's going on. So I'm just giving you a little bit of an idea of what the error messages look like. Okay, so this random matrix, it has 3 rows and 4 columns. So Mani has talked about matrices having numbers of rows and columns. It has 3 rows, 1, 2, 3, 4 columns. Okay, so you index into matrices with square brackets. Don't move around. And so we want the entry in the first row and the second column of the matrix, which is bracket 1, 2. If you know MATLAB, because you've had engineering 101, you're always going to put parentheses in there, and it's going to be super frustrating until that reflex goes away. I still make that mistake, okay? Because I have 30 years almost of MATLAB use, okay? So I'm very much into the syntax of MATLAB. But it's in Julia, you use square brackets to index into the matrix. Okay, so I think that part is pretty easy. The parts that takes a little bit getting used to if you haven't done it before is how you grab entire columns or entire rows. And if you want to select the 4th column of the matrix, that means we want all of the entries in the rows. And if you just put a colon in there, that allows you to do it. So bingo. This gives us the 4th column. So there's 1, 2, 3, 4 should start with 0.57, et cetera, and sure enough. So the colon is what allows you to take all of the rows. And we'll see later, if we only wanted the first 2 rows, we'd put 1, 2. But this is short, as we explained just now. That single colon is really the same thing as saying 1 to end. So that's kind of cool. The last index in a row or matrix, you just say end. You don't have to plug in the 7 or get its length and find out the length is 17 and plug it in. If you just go 1 to end is automatically going to go all the way to, in this case, the last column. And if I had the end over here, it would take the end of the rows. Questions so far? Makes sense, almost? Okay, so this will get you the first row of the, now, okay, so here's the thing. So here we want the first row of the matrix, and so here's the first row. We want all of the columns to get the first row, but here's our matrix. The first row, it should be a row of 4 elements. And in Julia, when we do this, first row, all of the columns, it returns a column vector. Julia has this quirk that it has a favorite representation for vectors. The default is always a column vector. And quite frankly, it's a little bit annoying. But you can easily fix that, and this is what you do. If you only want a particular row, in this case the first row, you take the first row and all the entries until the first row. So it's a little bit extra to write until you get used to it, and then it becomes a reflex. And then here, you can either go 1 to n to get all the columns, or you can just use our colon, as we talked about before. And when you do this, magically, you get the row. You don't have to put a transpose on it or anything like that, okay? So these are just little things that in the beginning, quite frankly, they can be frustrating. But once you've gotten used to how Julia thinks, it becomes a reflex, okay? So it's kind of like when you're learning a foreign language and you come across the false friends and you go, oh, this must mean what it does in English, and you find out that it's exactly the opposite. Question. So I'm gonna let you speak it into the mic so that those online can hear you.
This is just a personal preference thing, but could you also put like the transpose operator at the end, and would it be equally as acceptable for you, or is that a?
Yeah, so the question is, the other way to get it, which we show here, is using the the apostrophe at the end as a transpose. And either one is fine, okay? Either one is fine. So it's almost like was said, it's almost a style issue. This is just a way to get it out directly without having to put here, if we had put a comma here to get the transpose, then we get this very fancy mathematical term called an adjoint that is taught in upper level math courses, and we get the row vector as well. So personally, return doesn't do anything. Personally, I kind of like this one a little. Well, this is my favorite. It's the shortest you can do it. That's my personal favorite. It's built up since I started learning Julia in June of 2020, okay? So I've got 15 months into this language compared to 30 years in MATLAB, so that's what's going on. So the indexing can be a little bit weird when you're trying to get rows out of matrices. You got to do something extra. When you're trying to get columns out of matrices, you don't have to do anything extra at all. Well, this idea of using a range of entries is kind of nice, okay, because you can take out entire blocks of matrices. So here's a matrix that Lou has put in here. And we notice if you look at the first 3 rows and the first 3 columns, that submatrix is kind of clearly different than the other entries because she put zeros in it, okay? And so this would be a block, and the block could be in the middle just as well, or it could be at the end, okay? So you can pick out all the entries in a certain number of rows and a certain number of columns. And the way you do that is by just saying my block is, here Lou is taking the first 3 rows of the matrix and the first 3 columns. She could have gone 2 to 4 here and 1 to 3 here, but she wanted to get all of the non-zero entries, and they were very conveniently in the 3 by 3 part in the beginning. So it's a way to select a block of the matrix, and sure enough, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so what we're doing when we have 1 to 1 here is we're really getting a sub-block, okay? So this is what Lou is showing here. We're going to get the element that's 2, 2, 2, 2. So this is going to take the second entry, the second row, and the second column. So it's overkill. You could have just put 2, 2, and it would have done that entry as well. But it's now a 1 by 1 matrix. Now it happens to be integer 64 because the matrix just had integers in it. There were no decimals, so it's not float 64. And the thing is, this is a matrix. And what we're going to show you down here is dividing a real number by a matrix. That doesn't work. You want to divide a real number by a number, you have to extract the number from the 1-by-1 matrix. And this is the thing, once again, for those who've learned a little bit of MATLAB, MATLAB treats 1-by-1 matrices as if they are scalars. So you don't have to do that. But here in Julia, this small block, okay, after I now extract, it only has one entry, is now a number. And here it's actually an integer. And so when you get this error, when you think you're dividing a number by a scalar, because hey, that's 1-by-1, that's a scalar, okay? So for us, that's a scalar. And it goes method, no method matching divide, okay, irrational number pi by the matrix 64. Matrix, it's 1-by-1, it's a scalar, please treat it like a scalar. And it doesn't, okay? Whereas here you extract, yeah, I'm gonna try to get 2 mics in here so I don't have to hold the mic when I'm letting Lou have the, or John use the lapel. And then when we run this cell, everything is fine. Okay, so we've extracted the number from the 1-by-1 block. This is just talking about the transpose, etc. And the thing here is column vector. We forgot to paste it into here. So I'm going to set the mic down. I'm going to grab column vector. Here it is. No roll away. Practice 1, practice 2. Mumbling in the background. There we go. There, now column vectors defined. So if you do the same thing, just go and paste, grab column vector and paste it in, or just create the vector 0, 2, 4, 6, 8. It's a column vector because we're using semicolons to separate the elements. And then this last little example of using the transpose will now work. So this is column vector with transpose. And once again, using the transpose as a way of when you want to get a row, great, I did the row. You don't have to do one to end here if you don't want. You can just do the grab all the entries. That's totally up to you. It's a question of style, and then you get the row, etc. Okay, Lou, why don't you guide them through the practice exercises. Huh? Okay, where's the thing? You have to turn it on. So it's off.
Okay.
I don't want to get too close because then we'll get into a feedback loop and they'll really hate us.
Okay. So I'm gonna go through the practice section, which is very similar to the homework. So.
And John and I are available to come around and help if you guys need help.
Just get you an impression how to work on the homework. So first, let's recall what we defined previously, which is a random matrix here. And so when you do your homework, you'll see something like this, and you have to delete the through error exception. And so before this, it says small number equals. This is just get you to know what is the variable it will get tested in the Autograder cell. So you can delete this and put your answer here, or you can directly put your answer here and delete the small number in the line 2. So for example, here we can see the small number, which is asked for select the smallest number of the random matrix. So as you can see, the smallest number, it's 0.01, which is the third row and the fourth column. So which we can see is when the matrix third row and fourth column. So run this, and so we have this self-check cells before the actual autograder. So you can run this cell to see if your answer is like correct or not. If this is nonsense, so it has a high probability the answer is correct, but there's no guarantee because we didn't give the exact answer in this self-check cell. So, but this is if you get some error in this cell, you probably don't want to directly run the Autograder cell when you do your homework. Just try to get the self-check cell work before you submit the homework. Okay, so for this case,
Maybe it's easier for me to be a better instructor, Lou, when I'm back here bugging you, okay? So let's see if people have a question here about what to do. And I can bring the mic around.
Yeah.
Okay, I guess we're all good, Lou.
Okay. Okay. And the next question is select the column containing the smallest number of the random matrix and return it as a row vector. So here we see we delete this and we put the rand matrix. So it asks us to select the column. So we need to first choose all the rows, and so it's a column in the row index. And for the column index, which is we can see which is smallest number is the fourth column. So we put 4 here, and again it asks you to return. The Julia will, if you run this, the Julia will get you, like you see, a column vector. So in this case, if you didn't, if you just made it wrong, and you can run this cell, it's gonna tell you the size of your answer is incorrect. For example, you can say the size of row vec, the first answer of the size should be 1. So it should be a row vector, which is 1 by 3 vector. But what your answer right now is 3 by 1. So you can read this error message to see what is wrong here. So for example, here you can say you need to put as a row vector, and you can add a transpose operation to this row column vector. And here you get a row vector, and this is nothing, and you can run the auto cell grader in the homework. Okay. This is okay.
Mike. So our online crowd can hear you and other people in the room more better.
Sure. So since you were, I think in this one, when you put rand matrix colon, comma 4, I understand that, but 4, you put that out by hand. If we were to do this for a larger matrix where we're not really expected to inspect all the numbers and find the lowest and find the smallest number by hand, how would we put in for 4? Like what would we put in place of 4 in order for this row vector to be created?
I I didn't get the question. So you mean?
Yeah, the question is, if the matrix is so big that you can't really just look by eye and see it's the fourth column. So there are tools in Julia, MATLAB, C, Python, all of these to do searching in the matrix and pull out indexes satisfying certain criteria. So that's a little beyond what we're trying to do right here today, but all those tools are there. Yep. I got your question? Yes. Covered, perfect. Okay, Lou.
Okay. Yeah, this is just the practice for how you select a column or an entry in a matrix by using the indexing. So you can use some, for example, some fand functions to get the index. And okay. So is there any question about the practice too? Or any general question for the matrix indexing or vector indexing? Okay. 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 We can go to the example 3, for loops. So some introduction. We declare a 3x3 matrix A, which has integer numbers here, and so we want to get the sum of all the entries in the primary diagonal of the matrix. So by primary diagonal, which means the entries on the, the element which has the same row number and the column number. For example, here the A indexing 1 by 1 and A 2 by 2. Those are the elements on the primary diagonals. So we want to compute the sum of those entries. So we just add the sum equals the 3 elements, selecting them by using indexing. And we got here 13. So if we declare a matrix has more dimensions, for example, 5 by 5, we can still expand this equation, just add another two entries, for example, A 4 by 4 and A 5 5. So this has question, if the matrix A gets bigger and bigger, for example, have 50 by 50 matrix or 100 by 100, we don't want to just manually add all these elements. So what we're going to do using Julia is we can use something called for loop.
We had a question in chat where you explained Autograder Cell.
Okay. Where to say the question?
Let me get chat open for you, Lou. I don't have it on the other screen here. We don't need to see this. Under more. No, here it is. Chat.
Okay.
Could you explain the Autograder Cell one more time? Is that the question, Sean, you're referring to?
Yeah, so those two cell, actually I should rename it as something self-check cell. So this, in the homework, this will not grade you by your answer. This just give you an impression if the answer is correct or not. So this actual autograder cell, you can't see anything from it, and you can't get any feedback except the final grade. So before you want to grade your answer, for example here, the small number, you can run the self-check cell. If this self-check cell, for example, there's TF1, TF2, they print nothing, there's no errors here, then this means your answer is more likely to be correct. So if you get an error here, like if I did this wrong, I run this, it gives the assertion error, then it definitely means the answer is not correct. So you don't want to directly run the Autograder cell when you do your homework. You probably first want to get this cell, there's no error on this cell showing up. Yeah.
Yeah, so the Autograder cells, that's part of the feature of LumiDesk. And when you get into CS courses like EECS 280, which is C++, and then databases 281, there's 400 of you in that class, and they just don't have an army of graders to go through and do it. So it's automated grading. And the thing is with these Autograder cells, the way it is in a LumiDesk, it doesn't even tell you if you got the answer right or wrong. You just run it, okay? And you just cross your fingers and hope. And what we're trying to do here is add a little bit of a filter before it so you can get an idea that things are really good. So if you pass the test that we put up there, 99% chance you've got it right, okay? You could have a wrong answer and still fall through and satisfy the little test that we're running, because we're trying to write the test in a way that you can't see the correct answer from it, okay? So that's the idea. So it's just to be, we think, helpful. But if it's frustrating, then we'll just rip that out and go back to just, hey, we'll just hope that we got it right and not worry about it. Does that help? Okay.
Yeah, it also actually helpful for your debugging your answer. For example, for this question, you actually select the wrong column, but you forgot to return it as a row vector. If you run the self-check cell, it will tell you the size is incorrect, so you can easily get back to your solution to change that. Yeah, that's just, it's more helpful when you do your homework. Okay. Okay, so go back to the for loop. So in Julia, the for loop is something when you want to do an operation for several times, like the same operation, probably on the different numbers. But also if you can do the exactly operation several times, you don't want to write the command several times, then you can use the for loop. The syntax here is for is the keyword. You have to write exactly this for, the case sensitive. So this iterator, it can be any variable. It can be I, k, just any variable you like. And in is also the keyword. You have to write the same word. And there's a range. In this course, usually the range is a range of numbers. For example, 1 to 10, or 1 to 100. In other programming, this range could also be a list of other things. For example, some strings. You want to iterate through the name in like Rob11, there's a name list. You want to go through, iterate the name in this class. So the range could be like a name list. But here, the range is just, usually we do this for the numbers. And if this range is a number, you can replace the in by the equal sign. This only works when the range is numbers. Okay. And when you write the for loop, you have to write the end as a keyword as well to end this loop. Yeah, this is unique because for other programming languages, sometimes it has a column here. Sometimes it has a predicate. Or sometimes it doesn't have the end. So you just have to remember what's the syntax for Julia. Let's say an example here. We just print the numbers from 1 to 10. Yeah, if you don't use for loop, you have to write this print 1 and print 2, print 10 one by one. So if you use this for loop, it could just write these operations in 3 lines. And we can run this. Yeah, we can see the k is just, so this for loop runs 10 times. In each iteration, the k just equals 1. In the second iteration, the k equals 2. And you just print this k on the screen.
K here is a dummy variable. You could say for x in 1 to 10, print x. You get exactly the same output. So you can call it anything you want. For my favorite variable in range, whatever, print my favorite variable, you'll still get that list 1 to 10. Okay, so it's not like Fortran, where Fortran was limited to I, J, K, L, M, N for integers and other variables. And, oh, Fortran, sorry, that's ancient. That's what I was taught as an undergrad, okay?
Another thing is the for loop. You use for loop, the operations here doesn't need to relate it to this variable k. For example, you just want to do something several times. So probably you just want to print, say rob11 is cool. Okay. Okay. So it's still, this can be anything. So it just means the k doesn't need to be used in the operation. And when the range is numbers, you don't need to, so for this one, the step size is actually 1. So that's not showing in this operation. You can also specify the step size here. For example, I want to get a range of 2, there's a start to the stop, and specify the step size as 2. So in this case, I only get the even numbers from 2 to 20. The step size means I skip 1 and I get the second one when I build up this range. And also you can say step size 4, just get the half number from the previous list. Another thing is the step size can also be negative. But in this case, you have to remember the start number need to be larger than the stop number. For example, here, you want to get a range from 5 to 1, and the step size is -1. So it will get 5, 4, to 1. But if you get it wrong, you say 1 to 5, it doesn't give you anything. Because when this is doing inside is the first time the k equals 1 minus 1. And it's smaller than 1, so it's not in the range of 1 to 5. So that's why it gets you nothing. Yeah, so what else? Any questions so far? So the step size here can be 1, it has to be integer. Can be 2, can be negative. Yeah. Also, another thing is this number, this stop is included in this range. So what I mean is when you run this 2, you actually get the 20. Yeah, in other languages, sometimes it will just get to the number 19.
Ooh, if you change the 20 to a 21 in class, what do you think is going to happen when she changed the 20 to a 21? Is it going to print 21 or is it not going to print 21?
It will not, because it's only print the even number.
Exactly.
Yeah.
That's what you wanted to say. Yeah. Okay. Yeah, so just play around with the start, the increment or step size, and the terminal and get a little idea. It's a way to do something over and over in a very compact way. This is really the start of programming, for loops and if then else statements.
Okay, so go back to the matrix diagonals. Now we can get a sum of the diagonals for a large matrix. For example, here we declare a 30 by 30 random matrix. If we are not using for loop, we're gonna write at least 30 comments. So, but now we can just write it in several lines. Here we use the k, iterate through 1 to 30, and we each time add the element in the diagonals to this sum. Yeah, so here you need to first initialize the sum as 0, and then add up each diagonals here, and you can see the final result. Yeah, you can also write as you can also write sums add equals, yeah, like this. So this plus and equal sign just exactly equals the fourth line.
Sort of like the difference between cannot and can't, okay? Well, it's just a contraction. I almost never use it because I'm not a C++ programmer, but everybody who does C++,
So,
they are embarrassed when you write out sums equals sum plus a of k comma k, okay? So it's a question of style and sophistication. In the beginning, keep it simple and make it work. But
yeah, this just when you see this, you can directly translate this as equals and put the variable in the left sign here, and the same thing here. It's just the same. Also, when you see this, it equals this. Okay, and yeah, I think we know how to use the for loops, so we can work on something a little bit complex, like we can use nested for loops. We declare the A matrix again, and right now we want to print all the numbers on and below the diagonal. So which means the primary diagonal is 159, and we want to print all the numbers on this diagonal and below this. So what we're going to do for this for loop? The most straightforward way is using 2 for loops, and one for loop is inside another for loop. So, for example, here, I is actually iterate through the row numbers. It's the first row, second row, and third row. And the j is the column number, right? But here, the column number, the range of this column number is not a fixed number list. You want to stop at the number exactly as the row number. Is there any question? So just The row you iterate through 1, 2, 3, but the column number, for example, in the first row, you only want to get the first element. In the second row, you want to get the 1, 2 element. So that's why the stop element, the stop number of this column should be the row number. Yeah, I think that's straightforward. Okay, so then you get all the numbers printed. Okay, some practice. So we work with a 10 by 10 random matrix here. If you set the set as the same, you will get exactly same random matrix. And the question is, compute the sum of the numbers on the matrix primal diagonal.
Yep, and we're not going to work it for you. You guys solve it now. If you have problems, we'll come around and help.
Okay.
How about that, Lou?
Yeah, okay, then I think I'm done. That's the example for me.
Yeah. So Lou's already helped you out. She initialized the sum to 0, and in your homework, that'll be the first thing you forget to do. You'll write the for loop perfectly, but you will not have initialized the thing that you're adding to, okay? Rookie mistake. I made it 1,000,000 times, but I don't do it anymore. I'm no longer a rookie in Julia. Programming in general, though I'm not really a programmer. Lou's much more of a programmer than I am. I'm a math guy. Okay. And so what you want to do is remove either, you can just comment out this line here instead of removing it, and then put your for loop. Okay, you got the answer on yours, Lou, so you can tell them what the answer is and see if you get.
The answer is 3.66. So the prompt is, Andrew said the answer is 3.66.
Did you get 3.66? Hey, anybody got 3.69? You haven't tried that one yet? That's fine. Nobody's getting graded. We're just trying to give you a little bit. Okay, so you want to have 4, I equals 1, 2. This was a 30 by 30 matrix, Lou? 10, for I equals 1 to 10. And then the end statement, and then in between, sums equals sums plus a of I, comma I. Or if you called your index k, then it would be a of k, comma k. And yep, your answer should be between these two numbers, is what Lou's telling you here. So the 3.66 passes those tests, and you're pretty happy. And if there was an Autograder cell, which there's not in the lab stuff, you would be going, I got that one. Okay, so the structure is really this, and it's your choice. Instead of being 30, this would be 10, and you can put I, J, K, my favorite index here, as long as you put my favorite index here, and you'll just add them all up. So that's the cool idea with for loops. And what you're going to see in lecture tomorrow is how to solve a certain class of systems of linear equations by essentially a for loop, okay? There's another illustration where you use a double for loop. And we'll let you work that one on your own. And if you have questions, post them in Piazza, and we will definitely take care of them. Or after we're done here, we're happy to hang out and let you guys work extra problems, and we'll help you. Okay, so another topic, we're going to show you how to cheat in Rob 101. We're all about solving systems of linear equations in the first part of the course, okay? We're going to show you how you solve big systems of equations, and we're going to do it in a way that you could implement it on real machines in real time, okay? Now, depending on if you have an autonomous vehicle, you can have essentially a supercomputer in the trunk, so you can run almost anything, and that's what they do. But if you have a little drone, you're on the MAV team, or you've got one of these, you've got these little bitty tiny computers, and they do not have a matrix library in there, okay? So this is one reason why you would want to use the methods we teach in our course, because they are pretty computationally efficient. Also, you will understand the method of solving it when we start doing something called forward substitution, back substitution, and LU factorizations. We're going to show you how to cheat, and this is how you solve simple problems. Use something called an inverse of a matrix. We just want you to have it here so that when you're doing your homework problems, you can just check them really quickly, because you have a system of linear equations. You guys learned how to transform that system of equations into AX equals B. And so if you have AX equals B, how do you solve for X? Well, we haven't taught you what it means to multiply matrices. We haven't taught you what it means to invert a matrix. Those are all things that we will get to in Rob 101 and clean it up and make it really absolutely positively clear. But you guys can mimic code and just get an answer and check it. And so there's this thing called the inverse of a matrix, that when the matrix is square, same number of rows and columns, and its determinant is not equal to 0, this inverse always exists, and it is unique. And once you learn about matrix times vector multiplication, you take that inverse matrix, you multiply it times the right-hand side, and you get the solution. So if AX equals B, if A were a scalar and X were a scalar and B, you would say X equals B divided by A, or you would say it was the inverse of A times B. Okay, so the same thing works, except if A were a scalar, you could also do B times inverse of A, and you'll find out that that makes no sense at all in the matrix case. But we haven't gotten to all that stuff in Rob 101, but this is just showing you how you can get the answer really easily, okay? So make a note of it, and then when you're on your drill problems, when you're trying to solve things, why not just check it, okay? And this is how you can check your forward and back substitutions. What we'll also teach you is that this method doesn't scale, and it's numerically not the best posed problem to do this inverse. So it's a lot more efficient to do the things we will teach you in Rob 101. And all we're going to do check here is, hey, what does it mean that X is a solution? Well, when I plug it back in, and when I learn what a matrix times a vector multiplication is, I should get B back, okay? That's what it means for X to be a solution. And here, we just check it. And there's no assert error, so it's true that AX minus B is equal to 0, 0, 0. So AX equals B. Cool. This is just for fun. So we're trying to put, John, this is now the official image you put before the wow part, okay? Ha! Japanese anime, what else could be more awesome and cool? So some of you have had calculus, some of you hadn't. So we'll just do a little bit. I'll explain some calculus. and a little bit of history. So this is nothing that's in the course. This is just for fun, okay? And you may not think it's fun, but I think it's kind of awesomely cool, and nobody explained anything like this to me when I was younger, so I'm just going to draw a circle. That is not the main thing we're going to do here, just draw a circle. Defining the plots command and all this kind of stuff, bingo. That's a circle, okay? And it's a unit circle. Oh, my computer behaved better when Lou was running it. Okay, it's a unit circle because there's the origin and the radius is 1. Now, something you learn in calculus, so maybe you're in 115 and you wouldn't be getting to this, but in 116 where you do integral calculus, you learn how to calculate area. So you guys know what the area of a square is, or rectangle, A times B, and you probably have learned areas of triangles and things like that, even if you have not had calculus, okay? Well, the area of this circle, because it's a unit radius, should just be pi, the number pi. And so how did the ancients go about trying to approximate pi? Okay? Well, they literally did this. They literally would triangulate, inscribe triangles inside of pi. So here's 20 of them. I should have numbered them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, okay? And you can calculate the area of each of these triangles, and if you add them up, it's an approximation of the area of the circle. And that's really what calculus is about. Calculus is about dividing things, and you'll make these circles smaller and smaller. So what's the area minus pi when we do 20 of these triangles? And it's not too bad. We're off by 0.05. Well, how about 200? Ooh, can you imagine doing that by hand? Well, up until Euler, the ancients, okay, we call them now, right? They were doing this by hand. And monks and stuff like that, they would kind of compete to who could compute pi to the most decimal points. And how they did the calculation was they would inscribe the circle with triangles, and then they would superscribe it with triangles, and then they would calculate the error. And if you got enough triangles, pretty soon that error difference gets really small, and you can bound the number of digits. And they got up to like 12 and then 40 digits of pi. Like that, okay? Can you imagine? That was your job, to calculate areas of circles and just add them all up, okay? So that's what they did. So you can imagine doing that. And so calculus literally is the art of summing up areas of small things to approximate much more complicated things. And so calculating the area of a circle is something you will do in Math 116, and you'll get an analytical formula for it, and life is beautiful. Now, what's the area of this heart? Who wants to do an analytical derivation of the heart and get it from calculus, okay? But we can do the same exact thing, okay? So this is the area to a rough approximation, 565, but let me illustrate it. So I'll do with 20, just like we did before. You see, I just triangulated the heart. You can see that I'm going to get an under approximation because I'm leaving out some parts of the heart here, because I'm being very careful to draw my triangles so that they lie strictly within the heart, okay? And now, instead of doing 20, I don't know, you want to do 2,000? Just because you can? That's a lot of triangles, okay? So, and that's how you can compute the area of the heart, okay? Just by adding up that many triangles. Oops. Oh, you're supposed to write your own code here, so that's why I got the error exception. Because in my version, I've already had done that. Okay, so you can just play around with it if you want. It's just a way of seeing how these for loops can help you do other things. And we're not using calculus, integral calculus and things like that, but I just thought it would be interesting to show how are people calculating pi, and this is a program that's emulating what the ancients did to get pi out to, in this case, we've got it out to 5 digits pretty much, okay? So that's the end of lab for today. We'd be happy to answer questions and things. Nobody's gonna go, wow, that heart was cool? So, I think I saw the hand here first, and then I'll get over there, so. You don't mind touching something that others have done?
I don't care. Do we submit this?
Yep, so the question is, do you submit anything from labs? So unfortunately, everything that we deliver through Julia, there is a submit button. You only submit Julia homework 1, 2, 3, 4, 5, 6, 7, 8, and 9. You do not submit the labs. Tribby, the validate button seems to be working this year. Have you played with it?
So I think a validate button, as far as I understand it, it only checks if you still have the throw error statement in there still, and if you're failing some of the like the assert statements in the autograder that you can see, and you're failing them. So the self-check cells, they'll catch the validate. So if you're failing them, it'll just print those out. So it's just a good check. You don't have to validate before you submit, but it's good to.
So let me see if I understood. So if I'm doing my homework and, you know, I'm passing these little tests that we are doing that you can kind of get nothing, nothing, nothing. Yes, that looks pretty good. And then I hit the validate button. And if it doesn't throw any errors, then I'm probably in good shape.
Yes. Yeah.
And if I hit the validate button and it says something is wrong here, I should probably go back if I really want all the points and try to correct that part. Yeah, so last year the validate button was not working and students still got like 95% on the Julia homework, so I wouldn't worry too much about it. But if you have the time, you can hit the validate button and it should find most of your errors if you have them, but there's no guarantee it gets all of them. So that's working this year. So then when you're done there, hit the submit. Do you get 1 submission or can you do 5 submissions?
You can do 100.
So you hear that? You've got it done as much as you think you're going to get because you've got a big assignment in physics. Hit the submit button. And then if you have more time, you know, because you got that physics homework done or whatever you were working on, you can improve your Julia solution and just submit again, and we only grade the most recent submission. So now, if your first one was the best one and the third one was not, then you're still going to grade the third submission. So we grade the grader just accepts the last submission. Have I told any lies, Tribby? Tribby says no, I haven't told any lies, so I'm trying to earn your trust. You're good now? Oh, okay.
Yeah, sorry.
That's cool. Other questions? Now, please bring questions to us in office hours. Please post questions on Piazza. Initial stuff, for those of you who've had programming experience, this may seem too easy. For those who've done no programming before, all this stuff of indexing and for loops takes a while to grasp and you need to practice. Don't feel that you're a dummy. It's just practice, okay? It's just like you're with somebody who played sports in junior high and now you're in high school picking something up, you got to work hard to catch up, okay? So that's what the first couple of weeks will be. We're bringing everybody together, but by week 3 or 4, I think you'll all kind of be moving at the same pace with the same knowledge. So if you've had programming experience, please don't get bored and quit on us. And if you haven't had programming experience, don't get frustrated and quit on us. Just talk to us. We're all here to help.